This is our last video on the 5th section of our introductory chapter on special factoring. And what special factoring actually is just looking at factoring that ends up in certain patterns. So the big ones that we're going to look at would be this first one. So I started out with the actual factors for you to see the pattern. The pattern, if you notice in both of these, the first entries match, the second entries match in both the sets of parentheses, first and second. One pattern you'll see is when the signs are different, and one pattern you'll see is when the signs are the same. So kind of these repeated parentheses give us some special patterns that we'll see. The first one, which you should be familiar with already, is called a difference of squares. And the reason we call it a difference of squares, if I FOIL this out, x squared plus 4x minus 4x and minus 16 gives you x squared minus 16. What you'll notice about a difference of squares, difference means subtraction, and squares means both terms are perfect squares. Difference of squares can be factored using this pattern where you see perfect square, subtraction. If you have all those conditions, what you'll notice is your parentheses, one's plus, one's minus, if you look at the original parentheses we started with, and then the first entry is the square root of the first term, the second entry in the parentheses is the square root of the second term. So if we see something like x squared minus 25, we can recognize difference. We've got a subtraction, it only works with subtraction, and then you have a perfect square and a perfect square. So our parentheses are one is plus, one is minus, and then I take the square root of x squared for the first term, which is x, first term in the parentheses, and the square root of 25 is 5 for the second term, or second term in our parentheses. So it's kind of just a quick check for you. You can get to the answer if you have a perfect difference of squares. So if you look at these examples, I'll walk through the last one here with you because I think that one might be the most difficult. But the other two I'd like you to bring to class tomorrow. But if you look at the first term here on my last example, square root of 16x squared, just double check and see, is that a perfect square? Well, 16 is 4 and 4, so that part's a perfect square. X squared is a perfect square because x times x, something times itself gives you that. So the square root of 16x squared is 4x. Square root of 49y squared, 49 is 7 and 7, so 7, and that gives me a pair of y's. So they were perfect squares. We have a difference in the middle. So 4x and 7y, 4x and 7y, and then one's plus and one's minus. So if you double check, you got perfect squares, and you have subtraction, difference of squares will work for you. So that's one pattern that can help you easily factor. Another set is so we have these repeated factors, and what that's going to look like once we have everything multiplied out, 3x and 9, x squared plus 6x plus 9. What this is called is a perfect square trinomial. And what that means, to tell if it's a perfect square trinomial, you have to have the first term is a perfect square, the last term is a perfect square, and we can use this pattern to factor if the middle term is 2 times the square root of the first times the square root of the second. And I'll put those in parentheses so we can see the multiplication better. So if we look at x squared plus 6x plus 9, we know this is a perfect square trinomial. If we were given that problem in order to factor it, we'd say, okay, the square root of the first term would just be x, 1x. The square root of the second term would be 3. So that middle term better be 2 times 1x times 3. And it is, so we know that's a perfect square trinomial. So if we look at this term, or sorry, this next example here, if we're going to try and factor this, we say, okay, perfect square and a perfect square, but does that middle term match? So 4x squared, the square root would be 2x. 9, the square root would be 3. So 2 times the first square root of the first term, square root of the second term should give you that middle term if it's going to be a perfect square trinomial. So 2 times 2x is 4x, times 3 is 12x. So that checks out. That middle term is a perfect, or works out with our perfect square trinomial pattern. So if we write this as a perfect square trinomial, it's repeated parentheses, 2x and 3 addition, 2x and 3 addition, and we know it's addition because that middle sign here, because we know that the only way we're going to get positive 12 is by adding positive numbers here. The positive in the back tells you the same signs, and this positive in front of your second term tells you what sign is repeated. So we look at some examples here. This one I just wanted to check out and see if we can figure out what should go in that question mark blank. How would I know if this is a perfect square trinomial? I have a perfect square and a perfect square, but what should go in that question mark? So it should be 2 times the square root of the first term, which is x, square root of second, or our last term, which is 5. So what number should go in there? It should be a 10. That's how we're going to make that into a perfect square trinomial. If it was a 10 there, we could say x plus 5 times x plus 5. The square root of the first term, square root of the second term, and same signs. I'm going to do the second one with you and then leave the last one for you. Make sure you check and see, is it a perfect square trinomial? So the first term, square root of the first term would be 4x. Square root of the second term, or sorry, the last term would be 3. Is that middle term 2 times the first term square root and the third term square root? 2 times 4x is 8x times 3 would be 24x. So that's a match. Remember, the last sign here tells me the signs are going to match. So I have my square root of my 2 terms, the first and the third term. And the signs, because they have to match, so we have to have a positive 9 here, but we need negative 24, we're going to have to make both the signs negative. So that sign in the middle tells you, only when we're dealing with perfect square trinomials, that sign is going to, what that sign is going to need to be. So double check this last one, make sure it's a perfect square trinomial, and try it on your own. Pause the video here to try it. Last example that we don't see a whole lot of, but realizing that there is this sum and difference of cubes. So difference again means subtraction, sum meaning addition. If you have 2 cubed terms, they actually can be factored, and in some cases you'll be able to factor them in multiple steps. But here would be the pattern. We're not going to do a whole lot of examples with these, but realizing that you can do this with sums and differences of cubes. If you notice a cubed, this is just telling you have a cubed terms either added or subtracted. So what this is really saying is to factor this a cubed and b cubed, either addition or subtraction. What it's really saying is you want to take the cube root, and notice the signs here. The signs of your first set of parentheses is going to be, so it's plus or minus, and what you're going to do here is you're going to keep the sign you started with. And then you're going to write the cube root of the second term. So cube root plus or minus depending on what you had, addition or subtraction. And then we're going to take the cube root of your first term squared. And then notice the signs here. we have a plus or a minus, and notice, what do we have? We have, you switch the sign. And then we're going to have cube root times cube root. So A and B were both our cube roots. So cube root times cube root. And then our last signs here are going to be addition. So always addition. Always add. And then your last term, your second term, cube root squared. So what does that look like in an actual problem? In an actual problem, it looks something like this. So we want to know, what do we need to know in order to do this problem? We need to know what's the cube root of the first term. So cube root of 8x cubed. 8 is 2 and 4, 2 and 2. So this would be 2x. And the cube root of our second term, cube root of 27 would be 3. 3 and 9, 3 and 3. So if we're going to factor this, we're going to write this factored. It's going to be your cube root, and here, if you remember the first one, we keep the sign, minus your cube root. Your cube root squared, your first cube root squared, so 2x squared would be 4x squared. We change the sign, we do the opposite sign. Plus, and it was your cube roots times each other, so 2x times 3 was 6x, and then plus your cube root, your second cube root squared. So 3 squared is 9. Kind of ugly, but realizing that you can do this for sums and differences of cubes is the important thing. At times, this quadratic we're left with may be factorable, but in this case, it's definitely not, because we would say 4 times 9 is 36, and there's nothing that multiplies to be 36 that adds to be that middle term, positive 6. So I'm going to leave you with this one to try. It is a difficult thing doing sums and differences of cubes, but if you come in prepared to try this tomorrow, that'll definitely help you out. So this is the end of factoring, our basics for factoring, just some tips, some helpful hints for finding some patterns. See you on Tuesday.